All right, so let's take a look at that problem. All right, so in this problem, let's find the dimensions of a closed right circular cylinder can of smallest surface area whose volume is 16 pi cubic centimeters. Okay, so for this particular problem, okay, so we are trying to look for the dimensions, and we know the volume, and we're dealing with the smallest surface area. So we're going to let our function f of x, y, well, it won't be that. So we're going to have our surface area formula, okay, and then we have our volume. All right. So volume for the cylinder, right cylinder, is going to be pi r squared h. Okay, and we're going to subtract 16 from it since we know what that is. Okay, and for the surface area, and I got to think about that. So we're going to have 2 pi r squared plus 2 pi r h. Okay, so we're going to have those. All right. So if we find the gradient of s, okay, we're going to end up with 4 pi r plus 2 pi h in the I direction plus, don't need the parentheses here. We're going to end up with 2 pi r in the j direction. And then if we do the gradient of v, we're going to end up with 2 pi r h in the I direction plus pi r squared in the j direction. Okay, so now we're going to set up our Lagrange. So we've got the gradient of s is equal to lambda times the gradient of v. So one equation we're going to have is going to be 4 pi r plus 2 pi h is equal to 2 pi r h lambda. And our second equation we're going to have is 2 pi r is equal to pi r squared lambda. Okay, so we have both of those. Let's see here. I'm going to deal with this side first, okay, because it's going to be a little bit easier to work with. So I'm going to get it equal to 0, but I'm going to go ahead and remove the pi's from it, okay? So I'm going to have that 2r minus r squared lambda is equal to 0. So I can factor out our r, and I'm going to get 2 minus r lambda is equal to 0. Okay, so we get one case that r is 0. And then for the other, we can get that 2 minus r lambda is equal to 0. Okay. So essentially what I can do is I can solve this piece for lambda. So lambda is going to be 2 over r. Okay. So what I'm going to do now is to take that and I'm going to plug it into, if I do that, what does it do? Hold on a second. See, these are going to cancel. I'm fine with. Okay, so we have that. All right, so I'm going to end up with 4r plus 2h is equal to 2rh. Then in place of lambda, I'm going to put 2 over r. I don't want to, because if the case that r is 0, if I plug in 0 for r, I'm going to end up with h is 0. So if that's the case, then we don't have a cylinder. So that situation is going to be thrown out. So I have this, and what I'm going to end up with is 2r plus 2h is equal to 4h. Okay, and I'm just going to go to a new page real quick. So I'm going to have 2r plus 2h is equal to 4h. So it means that 2r is equal to 2h, so r is equal to h. So I know that r and h have to be equal. So I'm going to use this information and put it into dealing with the volume formula. So with the volume formula, we had that pi r squared h minus 16 is equal to 0. And it says that r is equal to h. So what we have is pi r squared times r minus 16 equals 0. So I can have that pi r squared, r cubed, excuse me, is equal to 16. R cubed equals 16 over pi. So r would be the cube root of 16 over pi, which we can't really do. And what did I say the answers was for this? Came out to be nice. Let's see if I did anything strange here. Oh, sorry. I see where my goof up is at. I decided to change something. This should have been still 4. Four. This is 4. So this should be 1/2 r. I mean 1/2 h. Or h is equal to 2r. This should be 2, 2. I think this should be 8. R equals. Now, my issue that I'm having is because I keep leaving things off. So R is going to be 2. There we go. So if R is 2, that makes H 4 in both cases centimeters. Okay, so it helps if I actually copy things correctly. So let me go back and look at everything. Okay, so here is our things. So the surface area for the um, cylinder, you've got two bases with circles, which is the pi r squared. So it's 2 times the two bases. So it's 2 pi r squared plus the side, and basically it's just the circumference times the height. So it's 2 pi r h. And then the volume should be pi r squared h minus 16 pi. I left off my pi here. Okay, so if we find the gradient of S, this is what we get. The gradient of V, this is what we get. And then we're going to have that the gradient of S is equal to lambda times the gradient of V. And here's our two systems. So here's the first equation that we got based on the I components. This is our second equation based on the J components. So I started working with the equation for the J components. And what I was able to do is to factor and solve for R and solve for lambda. Now, again, we're going to throw out R equals 0, because if R is 0, that's basically telling us that we don't have a cylinder. So I don't want that as a solution. Okay, so I look at the second piece and solve for lambda. So I get lambda is equal to 2 over R. And then what I'm going to do is to plug that into the equation that I have formed from the I components. Okay, so if I do that, again, what I did first was cancel out the pi's. So I have that 2R plus 2H is equal to 2RH times 2 over R, which simplifies down to 2R plus 2H is equal to 4H. And then that simplifies down to 4H. 4H plus 2H equals 4H. 4H is equal to 2H, or R is equal to 1/2 H. So now I'm going to use that and plug it into the volume formula. Okay, so we have that pi r squared H minus 16 pi is equal to 0. Okay, so in place of H, I'm going to put in 2R. So I got pi r squared times 2R minus 16 pi is equal to 0. So 2 pi r cubed is equal to 16 pi. Divide both sides by 2 pi. I get r cubed is equal to 8. So that means r is going to be 2. And we know that the height is twice the radius, so we get 4. So the radius is 2 centimeters, the height is 4 centimeters. Any other questions? All right, if there's no other questions, let's get started in where we left off at. Okay. All right, so we were working on area by double integrals. Okay, and we left off dealing with example 3. Okay, so in example 3, we're asked to find the area of the region bounded by x equals y squared minus 1 and x equals 2 y squared minus 2. Okay, so equals y squared minus 1 and x is equal to 2y squared minus 2. Okay, So if we're going to do this, again, the first thing we want to do, we want to do kind of a sketch of the region so we know what we're dealing with here. So if we graph this, both of these are parabolas that open to the right. Here, we're going to go over one, opening to the right, left one, open to the right. This one, we're going to go left two and opening to the right. Okay. Now, I don't really care that this is not exact. I just need a sketch of what we're dealing with here. So this is what we're dealing with here. So essentially, we're looking for this region here where they're enclosed. We're trying to find the area of this region. Now, we are going to set this up as a double integral. So what we're going to do when we set this up, so the area is going to be our double integral. Okay. Now, if we take a look at this, we notice the equations are x equals. Okay. So it will make it easy to integrate for x first, then integrate for y. Okay. Now, the reason I don't want to do y first, because then that would make me have to put my limits of integration in terms of y equals. Okay. And if we look at these equations, you cannot solve for y easily. Okay. So we wanted to stay as x equals. So that's why we want x first, then y. Okay. Now, for y, we can find that easily. And keep in mind the y are going to be numbers because we need that in order to be able to find the area. So in order to be able to find those values for y, we're going to set the equations equal to each other and solve for y. So we're going to have that y squared minus 1 equals 2y squared minus 2. So I'm going to subtract y squared, add 2. So I'm going to get 1 is equal to y squared. So that makes y plus or minus 1. So that's our limit, that's our values for y. So we're going to go from -1 to 1. Now, our values for x are going to be the function. Okay, so what I'm going to do is I'm going to draw a horizontal line in the region. So here's my horizontal line. Now, the way you're going to do this, okay, we need to define what the lower limit's going to be. We need to define what the upper limit's going to be. So what you have to do, you have to ignore how we set up for area in terms of when we were doing it as a single integral. Because when we did it as a single integral, we did right minus left. Okay. But as a double integral, if we're doing the lower limit to upper limit, we need to determine what's on the left because that will represent the lower, and then what is on the right will represent the upper. Okay, so based on the graph, okay, what function is on the left?
A is equal to 2y squared minus 2.
Right, so 2y squared minus 2 goes here. And then what functions on the right?
Y squared minus 1.
And that would be the upper limit. Okay, any questions there? Okay, so let's evaluate this integral. Okay, so we're going to have the integral from -1 to 1, integral from 2y squared minus 2 to y squared minus 1 dx dy. So if I integrate the first time, I'm going to end up with, if I integrate with respect to x, I'm just going to end up with what?
X.
I'm just going to end up with x, and then evaluate it from 2y squared minus 2 to y squared minus 1, and then dy. So now I'm going to have the integral from -1 to 1. So it's going to be the top minus the bottom. Okay, so integral from -1 to 1. So if I simplify this, what will I get?
Y squared plus 1.
Say it again.
Y squared plus 1.
Careful.
Like negative y squared plus 1.
Yes. And then dy. So now I'm ready to integrate this. So if I integrate this, what will I get?
Negative 1 cubed over 3 plus y.
Yeah. Sorry, put the wrong variable. And we're going to evaluate that from -1 to 1. Okay? So if we plug in 1, we're going to get -1/3 plus 1 minus, if we plug in -1, we're going to end up with 1/3 minus 1. So if we simplify, we're going to have -2/3 plus 2, or this is going to end up giving us 4/3. Any questions? Okay, so let's look at the next example. All right, so example 4. All right, so in here, we've got the integral from 0 to 3, and we've got the integral from -x to x times 2 minus x. We're doing dx dy. I'm doing dx dy. I'm sorry. It's a typo on the sheet. It can't be dx dy. It has to be dy dx. That's much better. It has to be dy dx. So one of the things they want us to do first is to sketch what the region looks like based on the limits of integration. Okay, so if we do that, okay, since x is second, we know x is running from 0 to 3. So we're starting off with 0, 1, 2, and 3. Okay, so we know what x is running. So now what we're going to do is to deal with the inside, which is y. And keep in mind, these are equations y equals. Okay, so we're going to deal with one function at a time. So we're going to run the bottom function first from 0 to 3. Then we're going to run the top function from 0 to 3. Okay, so starting off with 0. If we put 0 into the bottom function, what value do we get? we get 0. Okay, and then we're just going to keep going. So if we put 1 into the bottom function, what value do we get? We get -1. If we put 2 in there, what value do we get? And still in the bottom function. We get -2. And if we put 3 in, what value do we get?
-3.
Okay. So the blue is representing us working with going from 0 to 3 and plugging into the bottom function. Okay. So now what we're going to do is to work with just the top function. And again, we're going to go from 0 to 3. So if I put 0 into the top function, what value do I get?
0.
I get 0. Now, next I'm going to put 1 into the top function. So if I do that, what value do I get?
1.
1. Next, if I put 2 in, what value do I get?
0.
And then if I put 3 in, what value do I get?
-3.
Okay, so this kind of fuchsia represents the top function. Okay, so I have this point of intersection, which is 3, -3, and I have this point of intersection, which is 0, 0. Okay, so this is what it would look like, the region that I'm trying to find the area of. Any questions? All right, so what we're going to do now is to evaluate the integral. Okay, so if we evaluate the integral, the first time we're going to integrate in respect to y. So if we integrate respect to y, we're going to end up with the integral from 0 to 3 of what? Well, if we integrate respect to y, what do we get? Let me just say it that way. So what's the antiderivative of 1? Y, yes. And we're going to evaluate from -x to, I'm going to go ahead and multiply this out. So that's going to be 2x minus x squared. And then we're going to integrate respect to dx. So we're going to have the integral from 0 to 3 of 2x minus x squared minus a negative x, which is going to be plus x dx. So really, we're looking at the integral from 0 to 3 of 3x minus x squared dx. So if we take the antiderivative of this, what are we going to end up with?
Three squared over 2.
3/2 x squared minus
X cubed over 3.
Okay, so 1/3 x cubed, evaluated from 0 to 3. Now, the nice thing is that we don't have to worry about 0 because it makes everything 0, so we just need to worry about 3. So we're going to have 3/2 times 9 minus 1/3 times 27. So when we do this calculation, we should end up with 9/2 for our answer. Any questions? Right. Then last example in this section. All right. So the last example, we're looking for the average value for this. So we have a function f of xy. It's defined as 1 over xy. We're told that x is bounded between natural log of 2 and 2 times the natural log of 2. Y is bounded between natural log of 2 and 2 times the natural log of 2. Okay. So for the average value, we're going to do 1 over the area of the region times the double integral of f of xy over that region. Okay, so the first thing I'm going to do is to find the area of the region. Now, the nice thing about this is that it tells us in the problem that it's over a square. Okay, so the area of the region, since it's a square, is s squared. So we just need to find the length of the size. So we're told that x is bounded between natural log of 2 and 2 times the natural log of 2. Y is bounded between natural log of 2 and 2 times the natural log of 2. So how long is each side? So how long is each side? How long is that side?
I'll answer.
Right. So that's S. And there's our area. Any questions? Okay, next, let's deal with the double integral of the function over the region. So we're going to have the double integral. Our function is defined as 1 over xy. Now, how do you want to integrate? Do you want to integrate x first and y, or y then x? It doesn't matter.
Yeah, it doesn't matter.
So it doesn't matter with this. So we can go from dx then dy. Okay, so if we do that, we're going from natural log of 2 to 2 times the natural log of 2, natural log of 2 times 2 times the natural log of 2. And that was given to us already. Okay, so we're going to integrate the first time in respect to x. So we're going to have the integral from natural log of 2 to 2 times the natural log of 2. So if I take the antiderivative of this in respect to x, what will I get?
Ln x, y? Sorry, y ln x? Sorry, 1 over y ln x.
Right, 1 over y times the ln of x. And we're going to evaluate it from natural log of 2 to 2 times the natural log of 2, then dy. So now what I'm going to have is the integral from the natural log of 2 to 2 times the natural log of 2 of 1 over y times, if I evaluate this, it's going to be the natural log of 2 times the natural log of 2 minus the natural log of the natural log of 2 dy. But really, this is all but the natural log of 2 times the natural log of 2, integrating from natural log of 2 to 2 times the natural log of 2 of 1 over y times, what does this simplify down to?
Ln 2?
Right, dy. Okay. So now, if I integrate this, what will I get?
Ln y ln 2?
Okay. So we're going to end with the natural log of 2 times natural log of y. Evaluate it from natural log of 2 to 2 times the natural log of 2. Okay. So essentially what we're going to end up with is this. We're going to have the natural log of 2 times, if we evaluate it, we're going to have the natural log of 2 times the natural log of 2 minus the natural log of the natural log of 2. Now, we know that this is going to simplify down to what?
Ln 2?
And if we multiply those together, we're going to end up with the natural log of 2 quantity squared. So again, we're looking for the average value, and that's going to be 1 over the area times the double integral over the region of f of x, y, dA. So the area we found to be the natural log of 2 squared. This we found to be natural log of 2 squared. So our average value is going to end up being what? Yes, 1. Any questions? Okay. All right, so that is it with area, using using double integrals to do area. Okay. Any questions? Okay, so next we're going to move into dealing with double integrals in polar form. Okay, so we're going to move to double integrals in polar form. All right. So a couple of things that we need to remember. Okay, one, that x is equal to r cosine of theta. Y is equal to r sine of theta. Theta is equal to the tangent inverse of y over x, and that x squared plus y squared is equal to r squared. So just kind of going back and reconnecting on polar coordinates from Calc 2 and also from pre-calculus. Okay, so if we want to do area in polar form, right, it's going to be equal to the double integral over the region of r dr d theta. So area in polar form is going to be the double integral over the region of r dr d theta. Okay. So one of the first things we're going to take a look at is dealing with how to convert between from if we have a situation that is um, in rectangular form and convert it over to polar form to be able to integrate. And we need to have an understanding of this because sometimes it actually is easier to integrate in polar versus rectangular. Okay, so let's take a look. All right, so our first example we have is this. So we have the integral from -1 to 1. Then we have the integral from negative square root of 1 minus x squared to the square root of 1 minus x squared. We have dy dx. Okay. So in order to help us out with this, one of the first things we're going to do is we're going to look at a drawing of this. Okay, so if we look at a drawing of this, since x is second, we know that x is running from -1 to 1. Okay, then y is first, so we've got that y equals the square equals negative square root of 1 minus x squared, and then we've got y equals the square root of 1 minus x squared. So basically we have that. Now, the bottom piece here, oops, the bottom piece here, I'm not sure why that's moving like that. Bottom piece right here, what this is going to do is it's going to represent the graph of half a circle. Okay, and since it's negative, what it's going to end up doing is being the bottom half of the circle. And then y equals the square root of 1 minus x squared is going to represent the top half of our circle. So basically what we're looking at here is we're looking at dealing with a circle. All right. So now what we're going to do is to convert this to polar form. So to convert it to polar form, again, we're going to have our double integral. Okay. Now, the order that is going on with the polar, it has to be in this order. Okay. You cannot forget r. R is part of the equation of the formula. So you've got to remember that. dr has to go first, d theta goes second. And it always is going to be that order. Okay. So r, which is representing the radius. Okay. So if I look at this, the radius is going to start off at the center of the circle and then go out. Okay. So in the case of this, r is going to start off at 0 and it's going to go to 1. Okay. Now, theta is basically going to represent how long is it going to take to start from here and make it all the way around the circle. Okay. So when I first start off, theta will be 0. To make it all the way around the circle, I'm going to go to pi. Okay. Any questions there? So this is what our equation will look like in polar form. So now, if I evaluate this, I'm basically going to have the integral from 0 to 2 pi of 1/2 r squared evaluated from 0 to 1 and d theta. Now at 0, don't have to worry about it. At 1, I'm going to end up with just 1/2 in d theta. So now what I'm going to do is integrate this in respect to theta. So if I do, I get 1/2 theta evaluated from 0 to 2 pi. At 0 is going to be 0, so don't worry about it. So I just got to put in 2 pi. So I got 1/2 times 2 pi, or I get pi. And that would be my answer. Any questions? Okay, so let's look at the next example. All right, so next example, we have this. We have the integral from 0 to 2, integral from 0 to the square root of 4 minus y squared of x squared plus y squared dx dy. Okay. So again, with doing this, what I want to do is I want to take a look at this in terms of, I want to look at a graph of it so I know how to convert it correctly. So if I take a look at the graph of this, okay, the numbers from 0 to 2 are going to represent what values?
The y values.
Yes. So we're going to start on y at 0, then 1, then 2. Okay. And then from 0 to the square root of 4 minus y squared is going to represent what values?
X.
It's going to represent an x. Okay. So what I'm going to do is that I'm going to start with the lowest y value and then work my way up to the highest y value. So if y is 0, what will my x value be?
Plus or minus 2.
It cannot be plus or minus because you have to understand that this is not, it's just a principal square root. So unless it's got the minus in there, we can't include it. So all it should be is what?
2.
Just 2. Okay. All right. And then we're just going to go up to the top at 2. When y is 2, what's going to be the x value?
0.
0. So basically, you're going to get this. Okay. So now what I'm going to do is to do the conversion. Okay. So we're going to have our double integral. All right. Now, in the formula, you have r dr d theta. Now, in this, we have a little bit extra. Here's my extra. So in place of x squared plus y squared, what can I put in place of that?
R squared.
R squared. So I'm going to have to multiply this by r squared. Okay. So now what I want to do is my limits of integration. So first is r. So r is starting here and going out. So r is running from what to what?
0 to 2.
Okay. Then for theta is that if I start here and go to here, theta runs from what to what?
0 to pi over 2.
And this is our integral. Any questions? Okay, so what I'm going to be looking at is this. Okay, so I'm going to be looking at the integral from 0 to pi over 2, integral from 0 to 2 of r cubed dr d theta. So if I integrate in respect to r, I'm going to end up with 1/4 r to the 4th, evaluated from 0 to 2, d theta. Again, I don't have to worry about 0 because it is going to make it 0. So all I'm really concerned with is evaluating it at 2. So if I evaluate this at 2, I'm going to end up with a value of what?
Four.
Okay, so I'm going to end up with 4 d theta. All right. So now what I'm going to do is integrate in respect to theta. So I'm going to end up with 4 theta, evaluate from 0 to pi over 2. So at 0, don't have to worry about, but if I evaluate at pi over 2, what will I get?
2 pi.
And this will be my answer. Any questions? Okay, so next example. We have this. We have the integral from 0 to 1. We have the integral from 0 to the square root of 1 minus x squared. We have e to the negative x squared plus y squared dy dx. Okay, so what I'm going to do is I'm going to give you guys a couple of minutes to, one, draw the picture based on the limits of integration, and then two, rewrite it in polar form.
Sorry, I think you skipped number 3.
Did I skip number 3? I totally did. Okay, back up. So we're going to do this. Integral from 0 to 2, integral from 0 to x of y dy dx. Okay, but still the same thing. I'm going to give you guys a chance to see, one, draw the picture based off the limits of integration, and then set up the reset up the integral in polar form. I'm not worried about you evaluating yet. I just want you to do the setup. So I'll give you about 6 to 7 minutes to do that. Okay. Okay, so let's take a look at this. So starting off, we have that x is second. So if we look at that, we know x is running from 0 to 2. Okay, and then y is first, so y is running from 0 to x. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y will be 2. So this is what we're looking at here. Okay, so if we switch this over to polar form, we're going to have the double integral. Okay, now in place of y, we're going to put r sine theta, but we have to multiply that by, when we switch it over, r, then we have dr d theta. Okay, so now first for dealing with r. Okay, now with r, you have to understand that it's not, it's not the same. Okay, so what I'm going to do is just kind of draw some blue lines in. So here's where r is now. Then r changes as we go. Okay, so it's not always going to be the exact same length. Okay, so r is starting off at 0, but as it changes, okay, r is going to it's going to change. Okay, and what it's going to end up being is an equation for this line. Okay, it's going to be an equation for this line. So when we do this, and we have to be careful. Okay, so the equation of the line is for this is going to be that we know it was y equals x. Okay, so in place of x, we can look at x as, and I have to be careful here, x is set at basically 2. So let me look at this a little different. Okay, so we basically are trying to get over to here. So we're saying that x is equal to 2. Well, for x, you can rename it as r cosine of theta equals 2. Now, what we need to do is to solve for r. So we're going to divide by cosine of theta. So r is going to be 2 secant of theta. So that's what it's going to be on this. So it's going to be, the upper limit is 2 secant of theta. Okay, it's going to be 2 secant of theta. Now, for the next piece, and I'm just going to do a real quick sketch of the region. Okay, what I need to do is to find this angle that I'm going to have. Now, if I look closely at this, I know both legs are 2, so it's a right isosceles triangle. Well, a right isosceles triangle, what's going to be the measure of the 2 acute angles?
Pi over 4, 45
Right.
degrees.
So we're going to end up going from 0 to pi over 4 as far as theta is concerned. Okay, so this is a little sneaky in the way you would have to do this, because the other ones that we were doing circles, so the radius is always uniformed. But here, as we move up on Rx going up, it's basically changing. Okay, it's not always 2. Okay, the length is getting a little bit shorter as we go up as far as along the sides. So we're going to use the ending we are using the line x is equal to 2 to create our different values for r. Okay, and then here's what we did to solve for that. Right? Any questions there? Okay, so let's work on this problem to evaluate this. So we have the integral from 0 to pi over 4. Then we have the integral from 0 to 2 secant theta. And we have r squared sine theta dr d theta. So when we integrate the first time in respect to r, we're going to end up with 1/3 r cubed of sine theta evaluated from 0 to 2 secant theta d theta. So 0 is going to be 0, which is nice. So all we got to do is worry about 2 secant of theta. So we're going to have the integral from 0 to pi over 4. If I put in 2 secant of theta, I'm going to end up with 8/3 secant cubed theta sine theta d theta. So I can do a slight rewrite of this. So it becomes the integral from 0 to pi over 4 of 8/3. And what I'm going to do is pull 2 secants away. So I'm going to have secant theta times secant theta times secant theta sine theta d theta. Okay. So for this piece right here, for secant theta times sine theta, what is that equal to? Yes, that's going to be tangent of theta. So what we have is this, okay? So I'm going to have the integral from 0 to pi over 4. We have 8/3. I have 2 secants, so I'm going to put secant squared theta, then times tangent of theta, d theta. Now, for this particular situation, I can integrate it either way, and I'll stick at the same answer. I can integrate it in respect to I can do a u sub in respect to tangent, or split up the secant squared and use the u sub for secant theta. It doesn't matter. I'm going to do it with tangent as my u. So u is going to be the tangent of theta. So du will be secant squared theta d theta. Everything's there, so it's ready to go. Now, 8/3 is a constant times antiderivative of u, okay, it's going to be 1/2 u squared, and then we're going to evaluate that from 0 to pi over 4. Okay, and once again, at 0 is going to be 0, which makes it nice. So what I have is 4/3 times the tangent of pi over 4 squared. Well, what is the tangent of pi over 4? Yeah, it's just 1. So we got 1 squared, which is 1 times 4/3. So we end up with 4/3. And there's our solution. Any questions? Yeah. So let's take a look at our next example. All right. So for our next example, we have the integral from 0 to 1, integral from 0 to the square root of 1 minus x squared of e to the negative x squared plus y squared dy dx. So again, to help us be able to convert it over, what we're going to do is to take a look at use the limits of integration to set up to sketch our region. Okay. So for the outer, that's going to focus on what coordinates?
X.
For x. So x is going to run from 0 to 1. Okay. So as far as y is concerned, basically what we're going to do is just plug in the values. So when x is 0, we're going to get y is 1. When x is 1, y is going to be 0. So this is what we're going to get. Okay. So when we set up convert it over into polar form, we're going to end up with the integral, double integral. All right, so we're going to have r, we're going to have dr d theta. Okay, how are we going to rewrite the e to the negative x squared plus y squared?
E to the negative r squared.
Okay, e to the negative r squared. All right, so now based on our picture for r, what are our limits of integration in respect to r, for r?
0 to 1.
0 to 1. And then what will be our limits of integration for theta?
0 to pi over 2.
Right. Okay. Any questions there? Okay, so to do this, it is going to be a u sub. So u is going to be negative r squared. du is negative 2r dr. We're missing a negative 2, so we introduce that and bring out a negative 1/2. So when we integrate this, it becomes the integral from 0 to pi over 2. And then we're going to have negative 1/2 e to the negative r squared, evaluated from 0 to 1, d theta. Okay. Now, here, we do have to be careful in that we just cannot we cannot just get rid of 0. Okay. So essentially what we're going to have, I'm going to go ahead and factor out the negative 1/2. Then we're going to have the integral from 0 to pi over 2. If I evaluate at 1, I'm going to have e to the negative 1 minus. If I evaluate at 0, I'm going to have 1. And then d theta. So now I'm going to integrate this. So it's going to be negative 1/2 times e to the negative 1 minus 1 times theta. And we're going to evaluate that from 0 to pi over 2. Now, at 0, it is 0, so we don't have to worry about that. So we just have to worry about pi over 2. Now, if we plug in pi over 2, we're going to end up with negative pi over 4 times e to the negative 1 minus 1. And this would represent our solution. Any questions? All right, so got two more problems. Let's see here. Oops. All right, so let's take a look at problem number the fifth example. So here we've got the integral from -1 to 1. Then we've got the integral from negative square root of 1 minus x squared to the square root of 1 minus x squared. And then we're working with 2 over 1 plus x squared plus y squared squared dy dx. Okay, so again, what we want to do is to use the limits of integration to draw a region. Now, our region is already one that we've already done, so we know it's going to go from -1 to 1. 1. We got a lower half of the circle, then we have an upper half of the circle. So this is basically what we're going to have for as far as our region is concerned. Any questions there? So now what we're going to do is convert it to polar. So we're going to have our double integral. All right, we're going to have r. Now for this, we're going to write it as 2 over what?
1 plus r squared, the whole square.
Okay, 1 plus r squared squared. Then we have dr d theta. Okay, so now let's do our limits of integration. So the first set of limits of integration are going to be for r. What would those values be?
-1 to 1.
Not for r.
0 to 1.
Yes, it has to be from 0 to 1. And then for theta, it's going to be what?
0 to 2 pi.
Right, 0 to 2 pi. Any questions there? Okay, so we have this problem. How we're going to integrate this? Yes, it is going to be a u sub. So u is going to be what? One plus r squared. So that makes du equal to 2r dr. Well, we've got the 2r dr. So it's pretty much ready to go. So we're taking the antiderivative of u to the -2. Okay. So if we take the antiderivative of u to the -2, it's going to be -1 over u. Okay. Then we're going to evaluate this from 0 to 1, d theta. Okay. So the antiderivative of u to the -2 is -1 u to the -1 or -1 over u. Right? So if I evaluate this from from 1 to 0, I'm going to end up with the integral from 0 to 2 pi. At 1, I'm going to end up with -1/2 minus at 0, I'm going to end up with -1. So really, I'm looking at the integral from 0 to 2 pi of what?
1/2.
Okay. And so now I'm going to integrate 1/2 in respect to theta. So I'll get 1/2 theta. I'm going to evaluate it from 0 to 2 pi. So what will my answer be?
Pi.
So in this particular example, this is a prime example of in this problem, the way the problem is set up, there's absolutely no way that we will be able to integrate this in respect to x and y. Okay, so by doing the conversion, by doing switching it over to polar form, we are able to integrate it. Any questions? Okay, so now let's look at our last example. So our last example, we're asked to find the area of the common of the region common to the interiors of the cardioids. The two cardioids that we have are r is equal to 1 plus cosine of theta, and the second one is r is equal to 1 minus cosine of theta. Okay, so if I take a look at this, okay, so r is equal to 1 plus cosine of theta. Basically, it's going to start here. It's going to go a max of 2 over here. So we're going to come around, dip in, dip back out. That's going to be that particular cardioid. And then for the second one, it's going to be end up going a maximum 2 in the left side. So it's going to come around, dip through, around, and like so. Okay. So our common regions are these. Okay. So when I do this, okay, and I'm going to use polar coordinates, I'm going to do the double integral. Okay. So I'm going to do r dr d theta. Okay. And we are doing area. Now, if it was just x and y, we wouldn't have anything there. But since it's in polar, you have to remember that in the polar equation for area, r is part of the equation. So we have to have it in. Now, the way I'm going to look at this, I'm going to look at it a little bit different than what you expect. And what I'm going to use is I'm going to use this piece right here that I'm shading as blue as what I have. Now, I'm going to use symmetry to help me with this. Now, if I look at this, I notice that the y-axis splits everything up. So if I look at this carefully, how many pieces am I working with here?
4.
I'm working with 4 pieces. So what I'm gonna do is I'm gonna multiply this by 4. And what I'm gonna do is I'm gonna find the area for one piece. And once I find the area for one piece, then all I gotta do is multiply that answer by 4 and get all of them. Okay? Now, for that one piece that I'm dealing with, okay, it's using this second equation. So for that blue portion there, let's deal with theta first. How is theta running for that blue portion that I've got shaded? What's the start of theta? What's the end of theta? So here theta starting at what? at 0. Then we're moving, and theta gets to what? Pi over 2. So our limits of integration for theta are going to be from 0 to pi over 2. Now, for the radius, okay, the radius starts here. So the radius would be what?
0 to 1.
It's going to be 0. But it's not going to be 1, because if it's going to be 1, that means that it has a uniform shape. But it doesn't have a uniform shape. It's following along the curve. Well, which curve is it following along?
So
So it's following along which curve?
it's going to be secant theta.
No? Look at how it's going and look at my arrow. Following along which curve?
1 minus cosine theta.
Yes, it's following along the curve 1 minus cosine theta. So we're going from 0 to 1 minus cosine of theta. Okay. Now, I purposely didn't use the top one because then my R would have to be different, and my R would have to be different, and my theta would have to be different, because this portion right here is not created until later on with values of theta. I'm using this because it's being created initially really fast. So that's why I wanted to use this curve to help me write R instead of the first curve. Okay? And it just makes things easier to set up. And now I'm not saying that you can't do it. I'm just saying that it's easier. Right? Any questions? Okay, so if we evaluate this, what we're going to have is 4 times the integral from 0 to pi over 2. And if we integrate in respect to r, we're going to have 1/2 r squared, evaluated from 0 to 1 minus cosine theta, d theta. Okay. Now that 1/2, I'm going to go ahead and pull it out. So it gives me 2 here. Then I'm going to have the integral from 0 to pi over 2. Now in place of 0, it's going to be 0, which is nice. So I'm going to put in 1 minus cosine of theta in place of r. And I'm going to square that. Okay, so I have that. So now what I'm going to do is to fold that out. So what I'm going to end up with is this. 2 times the integral from 0 to pi over 2. If I square that, it's going to be 1 minus 2 cosine of theta plus cosine squared theta, d theta. All right, so I'm going to have to use a power reduction identity to rewrite this. So I'm going to have 1 minus 2 cosine of theta plus 1/2 times 1 plus the cosine of 2 theta, d theta. So now I'm going to go ahead and integrate this. I'm going to have 2 times. I'm going to have theta minus 2 sine theta plus 1/2 theta plus 1/4 sine 2 theta. And we're going to evaluate this from 0 to pi over 2. So if I evaluate at 0, everything is 0, which is nice. Okay, so I only have to worry about the pi over 2. So I'm going to have 2 times at pi over 2, I'm going to have pi over 2 minus the sine of pi over 2, which is 1 times negative 2 is negative 2. 1/2 of pi over 2 is going to be pi over 4. And then the sine of 2 times theta, that's going to be the sine of pi, which is 0, so I don't have to worry about that. So I'm going to have 2 times this plus this is going to give me 3 pi over 4 minus 2. Distribute, so I get 3 pi over 2 minus 4. That would be my area. Any questions? Now, one thing I will say is that doing area in polar form for double integral is a lot easier than it is with a single integral. Okay, um, you don't have to do so much extra stuff in order to get it to work. Okay, versus when you are doing with a single integral. Any questions? Okay, so that is it for today. All right, so you need to make sure that you are working on see, area as a double integral. And then double integrals in polar form. Okay. Also, quiz, I think it's 12. Let me make sure. Yeah. Quiz 12 is available and it's due on Thursday. Okay. So quiz 12 is available and it's due on Thursday. Okay. Any questions? All right, guys, you have a great rest of your day, and I will see you guys on Thursday.